Welcome to AI Frontiers, where cutting-edge research meets accessible insight. Today we explore the language revolution unfolding in artificial intelligence's quest to understand human communication. On October 30th, 2025, researchers published 39 groundbreaking papers in computational linguistics, revealing revolutionary attention mechanisms that reduce memory usage by 75%, new insights into how AI systems learn human values, and advanced mathematical reasoning benchmarks that expose significant capability gaps. These discoveries are reshaping the future of human-machine communication in ways that seemed impossible just months ago. Consider this mind-bending reality. Right now, as these words reach your ears, your brain performs one of the most remarkable feats in the known universe. Sound waves striking your eardrums transform into electrical signals, which somehow become meaning, emotion, and understanding. This extraordinary process represents the pinnacle of biological information processing. Yet researchers are now building machines that accomplish remarkably similar feats. The discoveries published on October 30th brought revelations that could fundamentally change how machines understand and generate human language, creating what amounts to a digital Rosetta Stone for the modern age. Computational linguistics represents the fascinating intersection where ancient human language meets cutting-edge artificial intelligence. This field bridges the gap between human communication and machine understanding, working at the crossroads of computer science and linguistics. Every interaction with Siri, every Google Translate query, every personalized social media recommendation relies on computational linguistics research. The field has evolved dramatically from simple keyword matching to systems capable of sophisticated conversations, poetry creation, code debugging, and complex problem-solving through step-by-step reasoning. This transformation mirrors the evolution from mechanical calculators to smartphones, with each leap bringing previously impossible capabilities. The digital Rosetta Stone concept captures the essence of computational linguistics perfectly. Just as the ancient artifact helped decode Egyptian hieroglyphs by bridging known and unknown languages, computational linguistics bridges human communication and machine understanding. Modern systems transcend simple pattern matching, engaging in sophisticated conversations, writing poetry, debugging code, and reasoning through complex problems. These advances represent a fundamental shift in how humans interact with technology, moving from rigid command-based interfaces to natural, contextual communication. The field continues transforming our relationship with digital systems, making technology more accessible and intuitive for everyone. Architectural innovation emerges as a dominant theme, with researchers questioning whether transformer architectures truly represent the optimal approach. This parallels architects discovering new foundation materials that support skyscrapers while using half the resources. The Kimi linear research exemplifies this breakthrough, developing hybrid linear attention architectures that outperform traditional full attention mechanisms while achieving 75% memory reduction and 6 times higher throughput for long documents. These efficiency gains represent more than marginal improvements. They constitute fundamental breakthroughs, making previously impractical applications feasible. The discovery resembles finding more fuel-efficient engines that actually deliver greater horsepower. Training dynamics research focuses on understanding how AI systems develop capabilities over time, resembling time-lapse photography of machine learning development. Rather than evaluating only final performance, researchers peer inside the training process itself, watching how systems grow and evolve. The Value Drifts research reveals surprising findings. Language models primarily acquire moral values during supervised fine-tuning phases, not during preference optimization that many researchers assumed was crucial. This discovery revolutionizes approaches to AI alignment, suggesting that careful curation of initial training data may prove more important than extensive post-training alignment procedures. These insights illuminate pathways toward more predictable and controllable AI development. Evaluation and benchmarking challenges intensify as AI systems become increasingly capable, rendering traditional measuring tools inadequate. The situation resembles attempting to measure skyscraper heights with rulers designed for furniture. The AMO Bench research addresses this challenge by creating mathematical problems meeting International Mathematical Olympiad standards. Even the best current models achieve only 52% accuracy on these problems, revealing that despite impressive capabilities in many areas, advanced mathematical reasoning remains a significant challenge. This finding highlights the need for benchmarks that can grow alongside AI capabilities, providing meaningful assessment as systems approach and potentially exceed human performance. 5 key discoveries from October 30th research are reshaping understanding of language AI fundamentals. First, comprehensive scaling analysis reveals that encoder-decoder models can achieve comparable performance to decoder-only architectures while offering substantial efficiency advantages, challenging widespread assumptions about architectural superiority. Second, investigation of relation decoding operators shows that language models store knowledge in property-centric structures rather than distinct relations as previously thought. Third, speculative decoding optimization achieves speed improvements up to 5.2 times over conventional methods. Fourth, mathematical reasoning evaluations reveal significant capability gaps. Fifth, value alignment research demonstrates that models acquire values during supervised fine-tuning rather than subsequent preference optimization. The linear research represents today's standout breakthrough, addressing the fundamental quadratic complexity problem plaguing language models since inception. Traditional attention mechanisms require computational resources that scale quadratically with sequence length, resembling dinner parties where every guest must personally greet every other guest, as complexity explodes with additional attendees. For years, researchers attempted developing linear attention mechanisms with better scaling properties, but these alternatives consistently underperformed compared to full attention. The field largely accepted that computational burden represented the necessary price of state-of-the-art performance. However, the team refused accepting this trade-off, pursuing breakthrough solutions. The hybrid architecture innovation represents the core of Kimi's breakthrough approach. Rather than completely replacing full attention, researchers created layered architectures combining different attention mechanisms strategically. This approach resembles designing buildings where different floors use structural approaches optimized for specific needs. The Kimi delta attention mechanism extends previous work with finer-grained gating, while specialized chunkwise algorithms achieve hardware efficiency through diagonal plus low-rank transition matrix variants. This mathematical innovation substantially reduces computation while remaining consistent with classical learning principles. The researchers engineered solutions based on deep understanding of theoretical foundations and practical constraints, creating sophisticated traffic control systems handling complex intersections efficiently. The revolutionary results validate the hybrid approach comprehensively. Researchers pre-trained models with 3 billion activated parameters and 48 billion total parameters, requiring massive computational resources and careful experimental design. Under identical training conditions, Kimi Linear outperforms full attention with substantial margins across all evaluated tasks. Efficiency gains prove equally impressive, up to 75% memory reduction and 6 times higher throughput for million token contexts. The team embraced open science principles, releasing kernel implementations, integration tools, and model checkpoints, enabling immediate community adoption. This breakthrough democratizes access to large-scale language modeling by dramatically reducing computational requirements, potentially making advanced language models accessible to organizations previously unable to afford deployment. Future horizons reveal exciting possibilities as researchers stand at the base of mountain ranges, where each peak represents different research challenges. Architectural innovations suggest entering a new phase of fundamental research into optimal language model structures. Hybrid approaches indicate that future progress may emerge from thoughtfully combining techniques rather than pursuing single approaches. Training dynamics research opens entirely new questions about capability development, potentially leading to more efficient targeted training procedures. Evaluation challenges highlight needs for assessment methods, keeping pace with rapidly improving capabilities. Efficiency research suggests futures where powerful language AI becomes more accessible and environmentally sustainable, with sophisticated models running on everyday devices, enabling previously unimaginable applications. The story continues beyond technical advances toward human-centered AI development. Hybrid attention mechanisms revolutionize efficiency fundamentals while training insights illuminate alignment pathways. New benchmarks reveal both impressive capabilities and remaining limitations, serving as stepping stones towards seamless human-machine communication. These discoveries represent more than technical progress. They constitute careful consideration of how advancement serves humanity's best interests. Researchers push boundaries while ensuring progress benefits society. The future isn't written solely by laboratory researchers, but shaped by everyone engaging with ideas and determining real-world applications. Each breakthrough builds toward futures where barriers between human and machine communication continue dissolving. This analysis was synthesized using advanced AI systems to process and interpret the latest computational linguistics research. The content synthesis utilized GPT Anthropic Claude Sonnet 42025 0514, while TTS synthesis was powered by DeepGram technology. Image generation utilized OpenAI systems throughout the production process. All content received review by human computational linguistics experts to ensure accuracy and accessibility. While every effort was made to present information accurately, some oversights may exist, and readers are encouraged to consult original archive preprint server references for complete technical details and verification of claims presented. Thank you for joining AI Frontiers today as we explored the revolutionary breakthroughs reshaping computational linguistics. These discoveries from October 30th represent just the beginning of a larger story about human-machine communication evolution. We encourage diving deeper into these papers yourself, engaging with the research community online, and considering how these advances might impact your work and interests. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archivepreprinserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archivepreprinserver.org.